So we're back to the bicentric Poncelet Triangle family. Let's animate it. P1, P2, P3, inscribing a fixed circumcircle, circumscribing a fixed incircle. Now I've picked a point Q on the circumcircle and I drew a tangent to the circumcircle at Q. We saw in a couple of videos recently that the isogonal image of this line with respect to this triangle was, let's try to draw this nicely, a circumparabola, which is a parabola, this red curve, which passes through the three vertices of my triangle. So I have a family of circumparabolas over Poncelet. Now, a quite striking phenomenon was that we noticed that over the specific Poncelet family of triangles, the locus of the focus of the circumparabolas is a straight line. Now today I decided to draw a new object on the screen, namely the polar triangle. Let's go ahead and place this in a better position. The polar triangle to this orange object here, the polar triangle to polar triangle of my reference triangle P1, P2, P3 with respect to, and when we say polar triangle we usually specify a conic, with respect to this particular circumparabola. So here's a polar triangle of P1, P2, P3 with respect to the circumparabola. A well-known property of the polar triangle is that its circumcircle contains a focus. So you can see this, that this is true. This has nothing to do with Poncelet, just a property of circumparabolas. And you can also think of the circumparabola to P1, P2, P3 as being the inscribed parabola to my polar triangle. Okay. Another very cool property of polar triangles is that their orthocenter is always on the directrix of the original parabola. So here's their orthocenter, here's the original parabola, inscribed to the polar, and x4 of the inscribed parabola lies on the directrix. I would like to thank Alexei Zaslavsky for letting me know about this really nifty property. So this has nothing to do with Poncelet, but if I animate a family, you're going to notice that x4 remains there. Okay. Now, what is the locus of x4 over Poncelet? You get a parabola. Okay. Now, quite interestingly, So I just want to say this, that the locus of x4 is a parabola, and I have not lit it up here, but I would love to know what the focus of this parabola is and whether it's something interesting. Okay. Okay. Now the cool result here is actually the locus of the barycenter. First of all, I'm going to show you guys what the locus of the circumcenter is over Poncelet. You can see here that it's this curve that could be a conic as well. Could be a sort of an everted parabola pointing outwards. Haven't tested that. But the really cool star here is the barycenter of the polar. Why? Because its locus is also a straight line. So as I move Poncelet, the locus of the barycenter of my family of polar triangles with respect to this family of circumparabolas moves along a straight line. Furthermore, this straight line is parallel to the straight line locus of the focus. So what is this distance? What is the angle? Very interesting thing. I mean, it seems like we might be stumbling upon a device, a geometric device that seems to be converting rotational motion, at least Poncelet rotations, into straight line motions. And that is done via the focus of the circumparabolas or via the locus of the barycenter of the polar. Another very cool feature here, I'm going to turn off the polar triangle for now, and I'm going to go back to basics. And I want to show you guys, so we had seen, for example, that the locus of the focus is a straight line. However, the locus of the vertex, this magenta curve, was not straight. And the locus of the reflection of the focus on the vertex, that center point of the directrix, was also not simple curve. But a cool thing happens when you actually draw the envelope of the directrix. It turns out the envelope of the directrix over Poncelet, and I don't believe I have talked about this before, over poristic family or n equals 3 bicentric, is a parabola whose focus is the incenter. So how cool is that? Let me actually superpose the locus of not the polar x2 as we had seen before, but I want to superpose the locus of the polar x4, and I'll show you why. The locus of the polar x4 closely resembles the envelope of the directrix itself. Now recall that I had just said that x4 of my polar lies on the directrix. It looks like both the envelope of the directrix and the locus of x4 are parabolas, and these parabolas are tangent to each other at some mysterious point. It's fixed right over Poncelet because one can only try to guess what this mysterious point is. It doesn't seem to be collinear with anything. It looks like it's around over here. And so many interesting phenomena here, right? Now let me actually show one other phenomena. So we're talking about going back to x2. Straight line locus of x2. Let's turn off this directrix envelope for a second. And I'm going to quickly switch to the family that has Poncelet family with an external circle and an internal concentric in ellipse. Notice how neither the locus of the focus nor that of x2 are simple curves, right? And I can go to x1 here. I can go to x3 of my polar family just to see if there's anything interesting. x3 looks rather complicated. Then you go back to x4, and it looks like x4 could be a parabola as well. And if you actually draw the directrix envelope, you're going to see again that you get very similar parabola. This one we know numerically to be a parabola, which is again tangent to the locus of x4 of the polar. Why is that? We don't know. Okay, last phenomenon. Let's clean this up. Let's get rid of this locus. Let's get rid of the directrix envelope and the focus locus. And we're going to switch to the family, the homothetic family. Now, homothetic Poncelet family of triangles interscribed between two concentric homothetic ellipses. They're actually the fixed Steiner ellipse, black one, and the fixed Steiner in ellipse. Their semi-axes are the in ellipses semi-axes are half those of the external Steiner ellipse. Now you can recall that there's a construction for circumparabolas as well that relies on the isotomic image of a line tangent to the Steiner. We talked about this in a previous video. So let's go ahead and here I've picked a point Q, right, on the Steiner. I've drawn a tangent, and I'm going to draw a circumparabola. So Q, and I'm not going to insert anything else right now. And this circumparabola again is the isotomic image of this infinite tangent line with respect to P1, P2, P3. So if I jog Poncelet, I get a different circumparabola. A first phenomenon that you notice is that all these circumparabolas are tangent to a line also tangent to the Steiner, but at a point which is the reflection of Q on the common center. So if I take this tangent here and I reflect it, mysteriously all these circumparabolas are tangent to this line over Poncelet. Okay, so if I change, for example, I'm going to change Q over here, you're going to get a different family of circumparabolas, but they continue to be tangent to that reflected line. Okay, and we saw in a previous video that focus locus was not a simple curve, neither was the vertex locus, neither was the directrix center locus. These three curves here were not simple. Recall that the green curve is a straight line in the bicentric family, right? Okay, now you get the following surprise. First of all, before I talk about the surprise, I can draw the envelope of the directrix. I thought I could. It's not letting me. Okay, so it doesn't want to generate the envelope of the directrix, maybe because of the position here. Could be. Let's change the position to see if we can do it, or this is a problem. Yeah, it looks like there's a bug in my code, and I can't generate the envelope of the directrix here. for some reason. But let's ignore that for now. This is not the main phenomenon. By the way, I just want to say that envelope is also a parabola. The main phenomenon is the following. I want to draw again the polar triangle. Now to this family, same idea as before. We have a family of blue triangles, a conic, in this case a parabola, and I can draw a triangle whose sides are tangent to this conic at the inscribed vertices P1, P2, P3. Conversely, this red conic is an inscribed parabola to my polar. Okay, now as expected, the circumcircle of the polar contains a focus. And in fact, if I draw its x4, it's going to be, as we expected, on the directrix of that parabola. So this is true dynamically, right? So if I move my Poncelet family, x4 remains dynamically on the directrix. This has nothing to do with Poncelet. This is just a property of polar triangles with respect to a parabola. Okay, now what I want to show here is that you get a very interesting phenomenon regarding loci. So the locus of x4 seems to be a parabola. Let's look at the locus of x1. The locus of x1 does not seem like a low degree curve. How about the locus of x3? Also not. x5 could be a parabola, and we could keep going on forever here, analyzing different loci. But the main one I want to show you guys is x2. Just like in the bicentric case, the barycenter of the family of polars here is also a straight line. And this straight line is parallel, not to my focus locus, but seemingly to the line tangent to the Steiner. So let's change that line to verify that this is the case. I'm going to go ahead and make it be 110, 115. Let's go in the other direction, 105, 100. So you can see here that the locus of x2 remains over Poncelet, a straight line. How do I know this is a straight line? I'm numerically checking. It's actually telling me the polar, the x2 of the polar triangle. I'm sampling on 33 points, and they're all collinear. So we go back to the bicentric case. Recall that the locus of x2 is also numerically collinear. I'm sampling this line here, 33 points, and it's giving me collinearity. So two new results, maybe three. The locus of x2 in both cases is a straight line. In the case of bicentric, it is parallel to the straight line focus, which is also unproven of the focus. And in the case of the homothetic, the focus of the locus of the homothetics is not a straight line, but the locus of x2 is a straight line, and it's parallel to that chosen tangent to the Steiner. The other curious result is, as we saw it, the envelope of the directrix over bicentrics is a parabola whose focus is the incenter. How cool is that? There you go, guys. Hope you've enjoyed it. I hope to see you soon again. Bye.